One of the things that's an ongoing difficulty for students in the WACE exam is this concept about constructing and balancing redox equations. So I've got my other video that you might have seen where it's balancing equations from scratch. But despite that, it still seems to be an ongoing problem. Year after year, the examiners put questions in about balancing redox equations, and students just seem to leave them blank or just look at them with some horror and going, I've got no idea how to do this. When actually the method is relatively simple, and it's important that you just approach it logically. It's not something you can memorize. You'd never be able to memorize all the reactions. In fact, they pride themselves on finding ones that aren't things you can memorize or aren't on the redox chart that you have at the back of your data book. So let's look at a couple from 2017, 2018, and 2019 to see how we go. So this is the question from the 2017 paper. Let's practice balancing this one from scratch. What we need to do first is identify the substances that are common. Alright, so if we look at this, SCN is on the left. Now, it's got sulfur in it, so that means it must be matched with a sulfate. It's also got carbon and nitrogen in it, so it must be matched with the HCN. What have we got left? IO3, ICl. Obviously, there's a chlorine there as well, so there has to be chlorine there. So, SCN minus going to sulfate plus HCN. There's one skeleton equation, and IO3 chloride going to ICl, another skeleton equation. Alright, so the rules are, rule 1, balance substances that aren't hydrogen or oxygen. In equation 1, sulfur is balanced, carbon is balanced, nitrogen is balanced. We need to balance, rule 2, balance oxygens with water. So if we add 4H2O, that means we have 4 oxygens on the left and we have 4 on the right. Rule 3, balance hydrogens with hydrogen ions. We have 8 on the left in that first equation and 1 on the right. So therefore we need another 7 hydrogens. Balance that out. All of the elements are now balanced. What is not balanced, however, is the charge. On the right hand side, we have minus 2 plus 7. So that's positive 5. On the left hand side, we've got minus 1. How do we get positive 5 equal to minus 1? We have to add 6 electrons. So that's now balanced. With the second equation, iodine is balanced, chloride is balanced. We have 3 oxygens left over. We need to balance those with 3 waters. We've introduced some hydrogens to the equation now. So now we need to add 6H+. All of the elements are now balanced. What we now need to be able to do is to balance the electrons. The charge on the right hand side is neutral. Charge on the left hand side is minus 1 plus 6. That all comes to be positive 4. So we need to add 4 electrons to make that neutral. Charges must be the same on both sides. Now we've got an equation that's got 6 electrons at the top and an equation that's got 4 at the bottom. So we need to make that a common factor, which is of course 12. So we times the top one by 2, bottom one by 3, and we put it all together. So 2 SCN minus plus 8H2O plus 3 IO3. So chlorides. There's our left-hand side components. So there's all our components. Now what we need to do is cross out anything that is on both sides of the equation, so the electrons go. We want to get rid of all those hydrogens and leave 4 of those behind, and all of those waters and 1 of those ones, leaving that behind. Now you can just leave it like that if you like to, or we can write it out as the final answer. There you go, 6 marks. Shouldn't be too scared of these ones. You should just work through them in a system and see how you go. Here's the 2018 version of this sort of question. They took a bit of a different approach this time and used an electrochemical cell as the basis of the question. Didn't ask you to do both equations, but in the end of the day, the actual techniques you need to use are exactly the same for this one as they were in the previous one, but a bit more reading required for this. So they've given you a fuel cell. You need to read the question very carefully. So we've got hydrogen gas here reacting with carbonate ions at the anode. Those things are very important. So you can see the hydrogen gas is here. Carbonate ions are going in here, and this is the anode. What's coming off is the CO2 from the water. At the other electrode, we've got some oxygen gas, and we're reacting with carbon dioxide gas at the cathode. So the oxygen gas is going in, the carbon dioxide gas is going in, and the carbonate is coming off. So the carbonate is the product from the cathode reaction, and it's one of the reactants at the anode reaction. Okay, so for the question, it says, write the half equation to show the reaction at the electrode in which oxidation occurs. Now, oxidation always occurs at the anode of a electrochemical cell. So for this one, we need to do the anode reaction. So from the question, we know that it's hydrogen gas, and it's reacting with carbonate ions, and it's producing CO2 and water as our two products. So we need to balance this equation for 3 marks. So hydrogen is balanced, 2 on the left, 2 on the right. So is oxygen, 3 on the left, 3 on the right, and so is carbon, 1 on the left, 1 on the right. So they're all fine. All we need to do is the charge. So the charge on the left is -2 and the charge on the right is 0. All we can do is add electrons to balance out. So we have to just simply add 2 electrons here, and we have a balanced equation for 3 marks. So 3 marks really is quite easy to get for that part as long as you've interpreted the question correctly. Now the second part is a little bit more difficult to get the same amount of marks for. Alright, so what they want is the overall. So with the overall, of course, you need to have the reduction equation to go with that oxidation equation that you can see there. So I'm just going to put this down the bottom. I haven't really left you much space for that. So with the reduction reaction, we've got oxygen gas going in, and we've got carbon dioxide gas going in purple there on the diagram. And what that's producing is it's producing carbonate ions. So we need to balance that equation. All right, so carbon is balanced. Oxygen is not, though. There's 4 on the left and there's 3 on the right, so we need to add 1 water to that to make that balance. Now, obviously, with introducing water, we've now put some hydrogens there that weren't there before, so we need to add 2 hydrogens into that half equation as well. And therefore, we're pretty close. All the elements are now balanced, but obviously the charge is not. +2 on the left, -2 on the right. The only way we can balance is by adding electrons. So if we add 4 electrons here, we have a total charge of -2 on the left, and we still have a charge of -2 on the right. So there's our reduction equation that we need. Now to balance and put them together, we need the same number of electrons given as are taken. So we need to times this one by 2 to ensure that we get 4 electrons given and 4 electrons taken, and then we need to write it out in full. So we've got 2H2 and 2 carbonates from that first equation, the oxidation equation, and we've got oxygen, and we've got CO2, and we've got hydrogen ions. We've got 4 electrons. There's our reactants rather. Now from a products perspective, we've got 2 CO2, 2 H2O, 4 electrons from the oxidation equation, and then carbonate and water from the reduction reaction. It's quite a complex equation, as you can see, but we can do a bit of cancellation. So if we go back to our equation, we can see that the electrons obviously will go first. Get rid of one of those carbonates, and we can get rid of one of those CO2s. So that means our overall equation for the 3 marks is 2H2 plus carbonate plus O2 plus 2H plus goes to 3H2O, because there's one here, there's one there, plus CO2. There's our overall equation for this particular question. Hopefully you can see that if you keep using this technique of balanced substances that aren't aren't oxygen or hydrogen, balance oxygen with water, balance hydrogen with hydrogen ions, and balance charge with electrons, you should be able to get this right every single time. What you don't want to do is try and scour the data sheet to find the equations. And you certainly can't take the data sheet and shoehorn another equation into one of these equations. You need to write them from scratch. 2019 had a similar question. There's usually a question like this in all the WACE exams. This one's slightly different again in terms of structure. The result is the same though, and it's asking you to give an oxidation and reduction half equation from an unfamiliar scenario. So what we've got is we have this equation here. Okay, so we've got calcium hypochlorite and hydrochloric acid. Now you won't find that on the data sheet. First of all, it wants the oxidation numbers. Okay, so and what we've got in this question is that the calcium hypochlorite and the hydrochloric acid are making chlorine and calcium chloride. So what's the calcium hypochlorite's, what is the chlorine's oxidation number in the calcium hypochlorite? So to answer this question, what we've got to do is start off with the fact that we know that calcium hypochlorite, let me write that in a color that you can see, CaOCl2, is actually made up of a calcium ion, because it's ionic, and it's made up of an OCl ion. Alright, now in OCl, we know that oxygen is always -2, so therefore the chlorine must be +1 in the calcium hypochlorite. In HCl, we've got it's covalent molecular material in terms of if it's a gas, but it's in solution. But hydrogen is always +1, so the chloride is -1, so it's -1 in the hydrochloric acid. So what's happening here is that the it says here in part B, write two half equations showing how the chlorine gas is produced from both substances. Oxidation half equation and the reduction half equation. So they've got a common product there. So Cl2 is the product from both reactions. Okay, so how do you know which one to go in which box? Well, if you remember that if oxidation number goes up, it's oxidation. So chlorine has an oxidation number of 0. So to go up, it must go from -1 to 0. So that's where the Cl- turning into chlorine is going to be the oxidation half equation. So if we add 2 there to balance it out, and we add 2 electrons here, we have a balanced oxidation half equation. For the reduction half equation, it's a similar story, although this one is particularly tricky, and a lot of students would get that quite wrong. So I'm just going to move that over there. Why is it so tricky? Well, this is why it's tricky. It's solid. So we've got to have calcium hypochlorite, and we've also got to react that with, we'll turn that rather into the chlorine. Okay, so now we need to balance it. So calcium hypochlorite going to chlorine. So first of all, chlorines are fine, no problems there. We've got to balance or account for our calcium ions, which are present in the calcium chloride solution. So that's fine. We need to add 2H2O to that to account for those oxygens. By doing that, we've added 4 electrons, or 4 hydrogens rather. 4 hydrogens go there. And now we need to balance it out for charge. Let's just check the atoms. 1 calcium, 1 calcium, 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens, 2 chlorines, 2 chlorines. So that's all fine. +2 charge on the right, +4 charge on the left, 2 electrons. That one's balanced. Particularly tricky because of that solid substance which you can't break up. So hopefully you can get familiar with this technique and be able to find some success with these questions.